So hello and welcome for today's session. So today we're going to talk about the transistors. So as we all know, the transistor is designated. So we are talking about the transistor called as BJT. So BJT stands for bipolar junction transistor. So if I write here, so this stands for bipolar junction transistor. So why do we call this transistor as a bipolar junction transistor? Because here both the charge carriers, that is the electrons as well as the holes, both the charge carriers will contribute in the flow of current. That is why we call it as a bipolar junction transistor. Whereas in the case of field effect transistor, there is only one type of charge carriers which is flowing from source to destination that we have seen in the module when we are discussing about the FETs. So there we have understood the working of FET. So now here we are looking the working or the flow of current in terms of the BJTs. So here ultimate goal of BJT. So here I have written the simple construction diagram of our BJT transistor. So here I have taken an example of a PNP transistor, emitter, base and collector. So as we all know, the two types of material are required to construct this transistor. One is a p-type material where the majority carriers are holes and minority carriers are electrons, and the another type of material required is the n-type material where the majority carriers are electrons and minority carriers are holes. So two p-type materials, if sandwich an n-type between the two p-type materials, so that will form the transistor. So that is a known fact that everybody knows it. So accordingly, there we have the two junctions that are formed here. So this junction we call it as the emitter base junction, and the another junction here we call this as the collector base junction. So normally when we look into the junction, normally the junction will be same, but the width of the collector base junction will be higher. Why? Because most of the time it will be in the reverse bias condition when we look into the active region. So uh, the transistor can be operated in any of these three regions. So the three regions that the transistor can operate is the active region, saturation region and the cutoff region. So the transistor can be in any one of these regions at any given time. So what do you mean by active region? So most of the amplifier designs which we do, so that is with the help of, or that is we'll do by making the transistor to work in the active region. So meaning of active region is that we'll make the emitter base junction as a forward bias and collector base junction as the reverse bias. So for emitter base junction, to make it as a forward bias, what I need to do is that I have to connect a positive terminal to this p-type so that it will become ripple and it will get positive, whereas the negative is negative. I have to connect negative to negative. So reverse bias is the case where I am connecting a positive terminal to a n-type region and negative terminal to the collector region where it is of p-type. So this will make this collector base junction as a reverse bias. So now this is in the active region. So here in this active region, what is happening is that the current from emitter is flown towards the collector with the help of the base. So now the base is controlling the amount of flow of current. So the current is here entering at the emitter terminal, and the small amount of current is coming out of the base, and the majority of the current will be going to the collector. So I will not be discussing more with respect to the minute or the micro level with respect to holes and electrons. So just understand here that let me write one more bigger diagram to make you understand how exactly this current flows here. So for example, let me write a bigger transistor diagram here. So this is my junction here, this is another junction, and this is a, yeah, I think it's not equally distributed. Yes, it's fine. Now this is my P and P. So when we make this emitter base junction as forward bias, what happens? These majority carriers nothing but holes that comes here, and it will start recombine with the electrons, but not all of them will recombine because number of majority carriers here in base are very less. the number of concentration, because as you can see there is a small area, so not all of the holes from P can be recombined with the electrons here, so very few of them can be recombined. So that is why what happens is that, so now few will recombine, and that will come out as the base current IB, that is a very small current. Now when the emitter base junction get reverse biased, so what happens, those holes which are entering here which have not recombined, that has become a minority carriers. Now due to reverse bias condition, what happens, there is a what do you say, that minority current flow. Now these holes which entered from P to N, now those have become like minority carriers, and now those minority carriers are again crossing this emitter based they are crossing the collector base junction and entering into collector region. So thereby the current is coming out from this, and this current we call this as the collector current. So ultimately our purpose is achieved, that is the purpose of transferring the current from the emitter to collector. So the name transistor has come because it is like transfer of resistance from input to output. So that is the meaning of resistor. So actually if you break into the parts, the actual term or the terminology of the transistor is the resistor. It means we are transferring the resistor from input to output. So what happens to the resistor here? So resistance level, if you look into here, it has the low input resistance and high output resistance. Why? Because here it is emitter base junction is forward bias and collector base junction is reverse bias. As in the reverse bias condition, you know, it gives a higher resistance. So transfer of current in the low resistance to high resistance. So this is about the introduction about the transistors. So now if you look into this case here, we will talk about the two types of current which are very important to understand the DC current if you talk about. So that is okay, before going to that, let me talk about something called configurations. So there are three types of configurations in which the transistor can be connected. So one is the common base configuration that we have already seen above in the circuit, and the other one is the common emitter sorry, BTT here, common emitter configuration. I'll just write config. Then the last one is the common collector configuration. So we have three types of configurations in which the transistor can be connected: common base, common emitter, and common collector configurations. So this type of configuration we call it as the common base configuration. Why? Because here the base terminal is common between both these bias. So here we are applying the bias, that is a forward bias, and here we are applying the reverse bias. So in both of these cases the base is common. So that is why it is called as common base configuration. If emitter terminal is common in both the bias, then we call it as common emitter, and the last one, if the collector is common, then we call it as the common collector configuration. So in common base configuration, the current factor is represented by alpha, and ideally its value is 1, but practically it is approximately equal to 1. It is not exactly equal to 1, it is approximately equal to 1. Why? Because when we talk about the currents here, so the emitter current will be always in terms of say milliamperes, whereas the base current is a very small current, so it will be in terms of microamperes. And again, when we talk about the collector current, it will be in terms of milliamperes. So both the emitter, base, collector, if we talk in terms of the current here, so the emitter current will be in terms of milliamperes, the base current will be in terms of microamperes, and collector current will be in terms of again milliamperes. Now, if you look into the common base configuration, here most of the current from emitter, it means most of the charges from emitter has been transferred to the collector, and a very small number of charges have been recombined in the base region, and we'll get a current like the base current. So that current is very small, microamperes. So then in such case, in common base configuration, what we can write is that uh, so if we neglect the base current, then IE is approximately equal to IC, because the base current is very small. If I neglect this, then I can straight away write IE is approximately equal to IC, or the current amplification factor alpha. With this, if I define, then um, the current factor or the amplification factor alpha, in this case it is defined as the ratio of output current by input current. So here, what is the output current that we are getting? So the output current here we are getting as the IC, and the input current is IE. So if I write this in terms of the ratio here, that is IC by IE, then if I rewrite this equation, then IC, the output current, is nothing but alpha into IE, alpha into IE. I already mentioned that the value of alpha in the common base configuration is 1 ideally, and practically it will be less than 1. So practically the value of alpha will be somewhere ranging from 0.9 to 0.999, something like that, 0.95, 0.98, 0.999, something like that, but not 1, because 1 is an ideal case. So then IC is equal to alpha into IE. Then I have written here the case, in this case approximately. So therefore, say if we consider the ideal case here, then I can write IC is approximately equal to IE. So that is how I have written this equation in this case. Okay. So this is about the common base configuration. So now let us talk about the common emitter configuration. So common emitter configuration is most widely used. Let me talk about a little bit on common base itself. I'll give more intuition. Common base configuration is fine, but what did we achieve from common base configuration? We have not achieved much with the common base configuration. Why? Because if you look at this, if I want to use my transistor as an amplifier, what should be my ultimate goal? My ultimate goal of being or utilizing my transistor as an amplifier is it should give the output in a boosted way, or the output signal should be amplified of what the input signal is given. If I use this transistor in the common base configuration, if you look into this equation, do you think that the output signal is boosted? Do you think the output signal is boosted? No. The answer is no. Why? Because the output signal is approximately equal to the input signal. It means the output current is approximately equal to the input current. So we will not get any amplified version of this signal of the input. So it means it is not recommended to use the common base configuration in the amplifier circuits. So common base may be used for some other applications. It might be in terms of oscillators or somewhere else. We will see that later. Or it can be used as a just normal switch where we can control the on and off operations. So now let us talk about the common base configuration. So if we talk about the common base configuration here, so then I'll going to write this in terms of the symbolic representation. So this is a symbolic representation of a transistor. So this is the emitter, this is the base, and this is the collector. And if you look at the symbol, this is my NPN transistor. So this is N, P, and N. So for NPN transistor, what I will do is that I'll make the emitter is a common between both the bias and here. So what I will do is that I have to make this forward bias and the collector junction as a reverse bias. So what power I need to apply? So I need to apply here the negative power. So I am applying the negative power here. Sorry for that. So negative power, then I'll connect this to this, and then I am applying here with a positive power here. So that is this. So this is the configuration of connection. So now if you see, the emitter is common between both the bias, external biases, which we have connected here. So this we call it as external bias. So now in this configuration, if you look into what is the input current here. So the input current is now the IB and the output current is my IC. So this is my equations. So now the current amplification factor in this common base configuration, it is represented by a factor beta. So now the beta is nothing but the ratio of output current by input current. So what is my input current here? So input current is IC and output current is the output current is IC and input current is IB. Now as I said before here, if you look into these things, so the IE and IC will be in terms of milliamperes and IB will be in terms of the microamperes. Now to understand this amplification factor, with the previous common base configuration, if the input current is 1 milliamperes and the collector current is 1 milliamperes, what is the alpha that we are going to get? We are going to get it as 1. Fine. Now in this case, to understand the amplification factor, if the output current, if you are getting here it as 1 milliampere and the input current is say 10 microampere, can you calculate and tell me what is the beta value? I don't have calculator. Can you please calculate? What is the beta value? Quickly. 1 by 10, it is millimicro. Anyone? Well, then I'll leave it to you because I don't have the scientific calculator right now. So I'll leave it to you to find out. Anyway, otherwise, the value of beta normally range from the value of beta is normally range from 50 to 400. So this is the range of beta. Now if you look in from the if you see this from the other direction, if I rewrite this equation here, if I rewrite this equation, then the output current, if I write, so IC is equal to, if I consider the value of beta is somewhere around 250, so this is beta into IB, right? Now if the beta is 250 into, say I'll consider this as a 10 microamperes, so if you multiply this, what do you get? So let me use the normal calculator and try to get the answer. So yeah, I think I don't need calculator for this. I'll just close it, it's simple value. So here I'll get 2500 microamperes. So if I see this, so it means I'll get this as 2.5 milliamperes. Did we get the amplified output or not? Yes, exactly. We got the output in the amplified form. You look into this, the input we have given as 10 milliamperes, output we are getting as 2.5 milliamperes. Definitely the output signal is boosted. That is why in most of the applications for amplifiers we go for common base configuration. So this terminal is grounded here. So where in the common base configuration the amplification factor is beta, which gives the output the multiplied factor of the input. So thereby we achieve the amplification signal. So this is in terms of DC. This is all fine. But our main concern is we will not apply the DC signal to get the level shifted. So in most of the applications, when we give the signal, it will be a sinusoidal signal. So if I give the sinusoidal signal, ultimately, because any message or any signal which we are transmitting, it will be a sinusoidal form, so that signal has to be amplified. So that we have to see whether we get that amplification factor or not. So now let us move for that analysis. So then let me write this here as BJT as an amplifier. So BJT as an amplifier, then this underline. So now when we are talking about the BJT as an amplifier, it means we are dealing with the sinusoidal waveform, not the DC waveform. So when we are dealing with the sinusoidal waveform, my terminologies will going to be changed. So here I'll be applying some input waveform, something like this, which is small variations of sinusoidal signal here. So this is my input, maybe VBB, and this is my Vin. Now what is the output that I need to achieve? So output I need to achieve here, it might be an inverted for some reason, that so I have to achieve this amplified version. So this is what I want ultimately at the output, at the collector terminal. So this is what we'll get. So if I write the circuit here, so circuit is a previous circuit which I had written is a very rough circuit where I have not taken into consideration the current limiting resistors and all. So now let us write a proper circuit here for a common base configuration. So this is my input source where I am applying the input signal, and for this to operate, first I need to bias this with the DC voltage. So DC bias is must, it is required. So I'll ground all the things here. So and here, so this is here, so then this is here. So there is one more current limiting resistor across the collector, we call this as RC. Connect. So this voltage source we call this as VCC, and this we call this as VBB. So this we call this as VBB, and this is my Vin, that is actual signal that I need to amplify. And this resistor we call this as RB, and this resistor we call this as RC. So now if you look into the voltages here, okay, I have done one small mistake here, so just I'm rectifying that. Actually I need to connect a positive polarity because I need to make this as forward pass. Sorry for that. Okay, so now if you look into the voltages here, so if we measure the voltage from this resistor point to here, what is the voltage? So it is a combined voltage of Vin and VB. So I can write this as VB plus Vin. So this is the voltage, and if I measure the voltage from this point to this point here, so this voltage is nothing but it is VCC plus Vn, VCC plus Vn. So this is the voltage. So now let us go for the analysis. So for the analysis I have to write back once again the same circuit here. So I'll quickly write the circuit and then we'll quickly jump onto the analysis part. So I'll rewrite the circuit here. So then here we have the circuit, and here we have the analysis. We'll write the AC equivalent circuit where we consider that the DC source is grounded. So I'll just ground the DC source. Sorry. We are doing the AC analysis here, so we'll ground all the DC sources and we'll consider only the AC sources that we have connected just for our analysis purpose. So this is the way of doing analysis. So what we need to do is that we have to ground all the DC sources initially. So this is RC and okay. So now what is the current that is flowing here is the base current IB here, and the current which is entering here, this is IC, and the current here, this is IE. So IE is almost 0. So I'll use the small notations because we are doing the AC analysis. So we'll use the small notations to represent the AC analysis. So that is represented as IE is equal to IB plus IC. So this is the notation. In case of DC, so we used to write this as in the capital form. The output current is equal to the sum of the base current plus the collector current, because this is true. Even we have seen before also, there are 3 currents which are coming here. As I told you, there is IE is the input current and 2 is the output current. So this is simply by the Kirchhoff's current law. We can write this IE is equal to IB plus IC. Now let us analyze this circuit here. So if we measure this voltage from this point to this point, we call this voltage as VC. Why? Because the emitter terminal is straight away grounded, so there is no emitter voltage here, and this is my collector point. So this voltage from collector to ground, this we call it as VC, and the voltage from base, so this voltage from here to here, this I call it as VB. That is the base voltage. So now in the analysis part, we know that IC is approximately equal to IE just a minute, hold on. So here. Okay, so here that we know that the emitter current is approximately equal to the collector current, then the collector current can be written as this is VB by RE dash. So RE dash is the emitter resistance, the internal AC emitter resistance. So let me write here. So RE dash is the internal AC emitter resistance. It's internal AC emitter resistance. So therefore I can define with the help of Ohm's law that I is equal to V by R. That is the current which I am getting here is VB by RE. Then the collector AC current, if we apply the KVL, here, then we can write this as that is VC is the current. So VC, if you look into the output voltage, so what is the voltage that is here? So output voltage is nothing but V is equal to I into R, simple Ohm's law again. So V is equal to IC into RC, which can also be written as, that is, because IC is approximately equal to IE, so I can write this approximately equal to, that is, IE into RC. Then my VB, the input voltage, is given by, now if I apply the KVL here, so my Vin also comes into picture, so it is like minus Vn. If I write that, so for example, let me erase this here, then So if I erase here, let me erase this. So now I'll get this here as, say, by applying the Kirchhoff's voltage law, it is minus Vn minus, what do we have, that is uh, IB into RE, IB into RB. So that is what I have here. Oh, I have written this as RE, sorry, this is my mistake, sorry for that. So this is actually, I have to erase this completely, come on. Okay, so this is actually the base resistance, this is RB, we can designate this as the RB, base resistance, not the emitter resistance. So it is minus RB with here this is positive and here this is grounded, so it is minus we have VB, which is equal to 0. So this is the from the Kirchhoff's voltage law when we apply to the input side of the circuit. So after that, if we rewrite this equation, then I'll get here as VB, I'll get the equation for VB is equal to Vin minus IB into RB. So this is what I'll get finally, the equation here. So now if we define the gain, so this is the equation for the output voltage and this is the equation for the input voltage that across the transistor here. So if we define the gain in terms of the voltage gain, then the voltage gain is the output voltage by input voltage, so I can straight away define this as a VC by VB. And if we try to simplify this and rearrange this, then we know that VC is equal to IC into RC, that can also be written as IE into RC approximately, and this is also IE by RB. So it means this IE get cancelled, so ultimately it is a ratio of the RC by, sorry, it is IE into internal resistance. This is what we have written here, that is IE is IE is equal to VB by so therefore VB is nothing but this one, sorry, it is not a capital RB, it is RE, internal resistance. So then IE get cancelled, so then it is RC by RE dash. This is the gain. So now if we want to define the current gain, so that is represented as IE, so IE is equal to IC by IB, which is equal to beta. So this is the current gain, and if we want to talk about the power gain, then the power gain is defined as the AP is equal to, now it's the product of the voltage gain with the current gain. So this is the small derivation with respect to this AC analysis or BJT as an amplifier. So if you have any queries, you can ask. So thank you for this session.